Good morning, good evening, good afternoon. Take your time, man. Or good evening, accept career. And next topic is the dynamics of Galileo and Newton. The profound breakthrough that the 17th century brought to science was the understanding of motion. The ancient Greeks had a marvelous understanding of things static, rigid geometrical shapes, or bodies in equilibrium, that is, with all forces balanced. So there is no motion, but they had no good conception of the laws governing the way that bodies actually move. What they lacked was a good theory of dynamics, that is, theory of a beautiful way in which nature actually controls the change in location of bodies from one moment to the next. But by no means at all of the reason was an absence of any sufficiently accurate means of keeping time, that is, of a reasonably good clock. Such a clock is needed so that changes in position can be accurately timed, and so that the speeds and acceleration of bodies can be well ascertained. Thus, Galileo's observation in 1583 that a pendulum could be used as a reliable means of keeping time had a far-reaching importance for him and for the development of science as a whole, since the timing of motion could then be made precise. Some 55 years later, with the publication of Galileo's Discourse in 1638, the new subject of dynamics was launched, and the transformation from ancient mysticism to modern science had begun. Let me single out just four of the most important physical ideas that Galileo introduced. The first was that a force acting on a body determines acceleration, not velocity. What do the terms acceleration and velocity actually mean? The velocity of a particle or point on some body is the rate of change with respect to time of the position of that point. Velocity is normally taken to be a vector quantity, which is to say that its direction has to be taken account of as well as its magnitude. Otherwise, we use the term speed. Acceleration, again a vector quantity, is the rate of change of this velocity with respect to time. So acceleration is actually the rate of change of position with respect to time. This would have been difficult for the ancients to come to terms with, lacking both adequate clocks and the relevant mathematical ideas concerning rates of change. Galileo ascertained that the force on a body, in his case the force of gravity, controls the acceleration of the body but does not control its velocity directly, as the ancients such as Aristotle had believed. In particular, if there is no force, then the velocity is constant, hence unchanging motion in a straight line would result from an absence of a force, which is Newton's first law. Bodies in free motion continue uniformly on their way and need no force to keep them going. Indeed, one consequence of the dynamic laws that Galileo and Newton developed was that the uniform straight line motion is physically completely indistinguishable from the state of rest, that is, absence of motion. There is no local way of telling uniform motion from the rest. Galileo was particularly clear on this point, clearer even than was Newton, and gave a very graphic description in terms of a ship at a sea. It is a reference to Drake 1953, probably PP is 186 to 7. Shut yourself up with some friend in a main cabin below docks on some large ship, and have with you some flies, butterflies, and other small flying animals. Have a large bowl of water with some fish in it. Hang up a bottle that empties drop by drop into a wide vessel beneath it. With the ship standing still, observe carefully how the tight little animals fly with equal speed to all sides of the cabin. These fish swim indifferently in all directions. The drops fall into the vessel beneath. When you have observed all these things carefully, have the ship proceed with any speed you like. So long as the motion is uniform and not fluctuating this way and that, you will discover not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still. The droplets will fall as before into the vessel beneath without dropping toward the stern. Although while the drops are in the air, the ship runs many spans. The fish in the water will swim toward the front of their bowl with no more effort than toward the back, and go with equal ease to bait placed anywhere around the edges of the bowl. Finally, the butterflies and flies will continue their flights indifferently toward every side, nor will it ever happen that they are concentrated toward the stern, as if tired out from keeping up with the course of the ship, from which they will have been separated during long intervals by keeping themselves in the air. This remarkable fact, called the principle of Galilean relativity, and is actually crucial in order that the Copernican point of view can make dynamical sense. Nicolai Copernicus 1473 to 1543 and the ancient Greek astronomer Aristarchus 310 to 230 BC, not to be confused with Aristotle, 18 centuries before him, had put forward the picture in which the sun remains at rest while the earth, as well as being in rotation about its own axis, moves in orbit about the sun. Why are we not aware of this motion, which would amount to some 1,000,000 kilometers per hour? Before Galileo presented his dynamical theory, this indeed posed a genuine and deep puzzle for the Copernican point of view. If the earlier Aristotelian view of the dynamics had been correct, in which the actual velocity of a system and its motion through space would affect its dynamical behavior, then the Earth's motion would surely be something very directly evident to us. Galilean relativity makes it clear how the Earth can be in motion, yet this motion is not something that we can directly perceive. Note that with Galilean relativity, there is no local physical meaning to be attached to the concept of at rest. This already has a remarkable implication with regard to the way that space and time should be viewed. The picture that we instinctively have about space and time is that space constitutes a kind of arena in which physical events take place. A physical object maybe at one point in space, at one moment, and at either the same or a different point in space at a later moment. We imagine that somehow the points in space persist from one moment to the next, so that it has meaning to say whether or not an object has actually changed its spatial location. But Galilean relativity tells us that there is no absolute meaning to the state of rest, so there is no meaning to be attached to some point in space at two different times. Which point of the Euclidean three-dimensional space of physical appearance at one time is the same point of our Euclidean three-dimensional space at another time. That was confusing. I didn't get it. What is? I have to read that line again. We imagine that somehow the points in space persist from one moment to the next, so that it has meaning to say whether or not an object has actually changed its spatial location. But Galilean relativity tells us that there is no absolute meaning to the state of rest. So there is no meaning to be attached to the some point in space at two different times. Which point of the Euclidean three-dimensional space of physical appearance at one time is the same point of our Euclidean three-dimensional space at another time. There is no way to say, okay. It seems that we must have a completely new Euclidean space for each moment of time. The way to make sense of this is to consider a four-dimensional space-time picture of physical reality. The three-dimensional Euclidean spaces corresponding to different times are indeed regarded as separate from one another, but all these spaces are joined together to make a complete picture of a four-dimensional space-time. The histories of particles moving in uniform straight-line motion are described as straight lines, called word lines, in the space-time. I shall return to the question of space-times and the relativity of motion later in the context of Einsteinian relativity. We shall find that the argument for four-dimensionality has a considerably greater force in that case. The third of these great insights of Galileo was the beginning of an understanding of conservation of energy. Galileo was mainly concerned with the motion of objects under gravity. He noticed that if a body is released from a rest, then whatever it simply drops freely or swings on a pendulum of arbitrary length or slides down a smooth inclined plane, its speed of motion always depends upon the distance that it has reached below its point of release. Moreover, this speed is always just sufficient to return it to the height from which it started, as we should now say the energy stored in its height above the ground, that is gravitational potential energy, can be converted into the energy of its motion, kinetic energy, which depends upon body's speed, and back again, but the energy as a whole is neither lost or gained. That brings a beautiful concept of Tesla coil. I don't know if it's a myth or if it's true, that he was supposed to provide electricity to the whole world. I read it somewhere, not sure where. Now, the law of energy conservation is a very important physical principle. It is not an independent physical requirement, but a consequence of the dynamical laws of Newton that we shall be coming to shortly. Increasingly comprehensive formulations of this law were made over the centuries by Descartes, Huygens, Leibniz, Euler, and Calvin. We shall come back to it later in this chapter and in chapter 7. It turns out that when combined with Galileo's relativity principle, energy conservation yields further conservation laws of considerable importance: conservation of mass and of momentum. The momentum of a particle is the product of its mass and its velocity. A familiar example of momentum conservation occurs with rocket propulsion, where the increase of a forward momentum of the rocket exactly balances the backward moment of less massive but compensating swifter exhaust gases. The recoil of a gun is also a manifestation of momentum conservation. A further consequence of Newton's law is conservation of angular momentum, which describes the persistence of a spin of a system. The Earth's spin about its axis and a tennis ball's each spin are both maintained through conservation of their angular momentum. Each constituent particle of body contributes to that body's total angular momentum, where the magnitude of any particle's contribution is the product of its momentum with its perpendicular distance out from the center. As a consequence, the angular speed of a freely rotating object may be increased by making it more compact. This leads to a striking but familiar action often performed by skaters and trapeze artists. The act of drawing in arms or the legs, as the case may be, causes the rotation rate spontaneously to increase simply because of angular momentum conservation. We shall find that mass, energy, momentum, and angular momentum are concepts that will have importance for us later. Finally, I should remind the readers of Galileo's prophetic insight that in the absence of atmospheric friction, all the bodies fall at the same rate under gravity. The reader may recall the famous story of Galileo's dropping various objects simultaneously from the Leaning Tower of Pisa. 3 centuries later, this very insight led Einstein to generalize the relativity principle to accelerating systems of reference, and it provided the cornerstone of his extraordinary general relativistic theory of gravity, as we shall see near the end of this chapter. Upon the impressive foundations that Galileo had, Newton was able to erect a cathedral of superb grandeur. Newton gave 3 laws governing the behavior of material objects. The first and second laws were essentially those given by Galileo. If no force acts on a body, it continues to move uniformly in a straight line. If a force does act on it, then its mass times its acceleration, that's the rate of change of its momentum, is equal to that force. One of Newton's own special insight was to realize the need for a third law. The force that body A exerts on body B is precisely equal and opposite to the force that body B exerts on body A. This provided the basic framework. The Newtonian universe consists of particles moving around in a space with its subject to the laws of Euclid's geometry. The accelerations of these particles are determined by forces which act upon them. The force on each particle is obtained by adding together, using a vector addition law, all the separate contributions to the force on that particle arising from all other particles. In order to make this system well defined, some definite rule is needed to tell us what the force on a particle A should be that arises from some other particle B. Normally, we require that this force acts in a direct line between A and B. If the force is a gravitational force, then it acts attractively between A and B, and its strength is proportional to the product of the two masses and to the reciprocal of a square of the distance between them, the inverse square law. For other types of force, there might be a dependence on position different from this, and the force might depend on the particles according to some quality they possess different from their masses. The parallelogram law of vector addition. They have a parallelogram law of vector addition over there. UV and their diagonal is U plus V. The force between two particles is taken to be direct line between two. The great Johannes Kepler, 1571 to 1630, a contemporary of Galileo's, had noticed that the planets' orbit about the Sun are elliptical rather than circular, with the Sun being always at a focus node at the center of the ellipse, and he formulated two other laws governing the rates at which these ellipses are described. Newton was able to show that Kepler's three laws follow from his own general scheme of things with an attractive inverse law of force. Not only this, but he also obtained all sorts of detailed corrections to Kepler's elliptical orbits as well as other effects such as the precision of the equinoxes, a slope movement of the direction of the Earth's rotational axis, which had been noticed by the Greeks over the centuries. In order to achieve all this, Newton had to develop many mathematical techniques in addition to differential calculus. The phenomenal success of his efforts owed much to his supreme mathematical skills and to his equally superb physical insights. The mechanistic world of Newtonian dynamics, with a special law of force such as the inverse square law of gravitation, the Newtonian scheme translates to a precise and determinate system of dynamical equations. If the positions, velocities, and masses of various particles are specified at one time, then their positions and velocities and their masses, this being taken to be a constant, are mathematically determined for all later times. This form of determinism, as satisfied by the word of Newtonian mechanics, had and still has a profound influence on philosophical thought. Let us try to examine the nature of this Newtonian determinism a little more closely. What can it tell us about the question of free will? Could a strictly Newtonian word contain minds? Can a Newtonian word even contain computing machines? Let us try to be reasonably specific about this Newtonian model of the world. We can suppose, for example, that the constituent particles of a matter are all taken to be exact mathematical points, that is, with no spatial extent whatever. As an alternative, we might take them off all to be rigid spherical balls. In either case, we shall have to suppose that the laws of force are known to us, like the inverse square law of attraction of Newton's gravitational theory. We shall want to model other forces of nature also, such as electric and magnetic forces, first studied in detail by William Gilbert in 1600, or the strong nuclear forces which are now known to bind particles, protons and neutrons, together to form atomic nuclei. Electric forces are like gravitational ones in that they also satisfy the inverse square law, but for which similar particles repel each other rather than attract as in gravitational case, and here it is not the masses of the particles that govern the strength of electrical forces between them, but their electric charges. Magnetic forces are also inverse square like electric ones, but nuclear forces have a quite different dependence on distance, being extremely large at the very close separations that occur within the atomic nucleus, but negligible at greater distances. Suppose that we adopt the rigid spherical ball picture, requiring that when two of the spheres collide they simply rebound perfectly elastically, that is to say, they separate again without any loss of energy or of the total momentum, as if they were perfect billiard balls. We also have to specify exactly how the forces are to act between one ball and the another. For simplicity, we can assume that the force that each ball exerts on each other ball is along the line joining of their centers, and its magnitude is specified function of the length of his line. For Newtonian gravity, this assumption automatically holds true by a remarkable theorem due to Newton, and for other laws of force it can be imposed as a consistent requirement. Provides that the balls collide only in pairs and no triple or higher order collisions occur, then everything is well defined and the outcome depends in a continuous way on the initial state. That is, sufficiently tiny changes in the initial state lead to only small changes in the outcome. The behavior of glancing collisions is continuous with the behavior when the balls just miss one another. There is, however, a problem with what to do with the triple or higher order collisions. For example, if three balls A, B, and C come together at once, it makes a difference whether we consider A and B to come together just first and C then to collide with B immediately afterwards, or whether we consider A and C to come together first and then B collide with A immediately afterwards, or a model there is an indeterminism whenever exact triple collisions occur. If we like, we can simply rule out exact triple or higher order collisions as infinitely improbable. This provides a reasonably consistent scheme, but the potential problem of triple collisions mean that the resulting behavior may not depend in a continuous way on the initial state. This is a little unsatisfactory, and we may prefer a picture in terms of point particles, but in order to avoid certain theoretical difficulties raised by the point particle model, infinite forces and infinite energies when particles come towards coincidence, one must make other assumptions, such as that the forces between the particles always become very strongly repulsive at short distances. In this way, we can ensure that no pair of particles ever actually do collide. This also allows us to avoid problem of deciding how point particles are supposed to behave when they collide. However, for ease of visualization, I shall prefer to phrase the discussion which follows entirely in terms of rigid spheres. It seems that this kind of a billiard ball picture is essentially the model of reality that a good many people have at the backs of their minds. Now, ignoring the multiple collision problem, the Newtonian billiard ball picture of reality is indeed a deterministic model. The word deterministic is to be taken in the sense that physical behavior is mathematically completely determined for all times in the future or past by the positions of velocities of all the balls. At any time, it seems then that there is no room for a mind to be influencing the behavior of material things by the action of its free will in this billiard ball world. If we believe in free will, it would seem that we are forced to doubt that our actual world can be made up in this way. The vexed question of free will hovers at the background throughout this book, though for most of what I shall have to say, it will remain only in the background. It will have one specific but minor role to play later in this chapter in relation to the issue of faster than light signaling in relativity. The question of free will is addressed directly in chapter 10, and there the readers will doubtless be disappointed by what I have to contribute. I do indeed believe that there is a real issue here rather than an imagined one, but it is profound and hard to formulate adequately. The issue of determinism in physical theory is important, but I believe that it is only part of the story. The word might, for example, be deterministic but non-computable. Thus, the future might be determined by the present in a way that is in the principle non-calculable. In chapter 10, I shall try to present arguments to show that the actions of our conscious minds is indeed non-algorithmic. Accordingly, the free will that we believe ourselves to be capable of would have to be intimately tied in with some non-computable ingredient in the laws that govern the world in which we actually live. It is an interesting question whether or not one accepts this viewpoint with regard to free will, whether a given physical theory is indeed computable, not just whether it is deterministic. Computability is a different question from determinism, and the fact that it is a different question is something that I'm trying to emphasize in this book. And there are many things to discover in this book, but the main point is something determinism or not? Is it algorithmic or not? Wow. Is the life in the billiard ball word computable? Let me first illustrate with an admittedly absurdly artificial example that computability and determinism are different. By exhibiting a toy model universe which is deterministic but not computable, let the state of this universe at one time be described as a pair of natural numbers m and n. Let TU be a fixed universal Turing machine, say the specific one defined in chapter 2, to decide what the state of this universe is to be at the next instant of time. We must ask whether the action TU on M ultimately stops or does not. Whether TU of M is not equal to square or TU of M is equal to square in the notation of chapter 2. If it does not stop, then it is to be n plus m and m. We saw in chapter 2 that there is no algorithm for the halting problem of Turing machines. It follows that there can be no algorithm for predicting the future in this model universe, despite the fact that it is completely deterministic. Of course, there is not a model to be taken seriously, but it shows that there is a question to be answered. We may ask of any deterministic physical theory whether or not it is computable. Indeed, is the Newtonian billiard ball word computable? The issue of physical computability depends partly on what kind of question we are proposing to ask of the system. I can think of a number of questions that could be asked for which my guess would be for the Newtonian billiard ball model that it is not a computable, that is algorithmic matter to ascertain the answer. One such question might be, does ball A ever collide with ball B? The idea would be that as initial data, the positions and velocities of all the balls are given to us at some particular time, and the problem is to work out from this data whether or not A and B will ever collide at any later time. To make the problem specific, we may assume that all the balls have equal radius and equal mass, and that there is, say, an inverse square law of force acting between each pair of balls. One reason for guessing that this particular question is not one that can be resolved algorithmically is that the model is somewhat like a billiard ball model for a computation that was introduced by Edward Fredkin and Tommaso Toffoli. In their model, instead of having an inverse square law of force, the balls are constrained by various walls, but they bounce elastically off one another in a similar way to the Newtonian balls that I have just been describing. In the Fredkin-Toffoli model, all the basic logical operations of a computer can be performed by the balls. Any Turing machine computation can be imitated. The particular choice of Turing machine T defines the configuration of balls, etc. of the Fredkin-Toffoli machine. Then an initial state of balls in motion codes the information of the input tape, and the output tape of a Turing machine is coded by the final state of the balls. Thus, in particular, one can pose the question, does such and such a Turing machine computation ever stop? stopping might be phrased in terms of ball A eventually colliding with ball B. The fact that this question cannot be answered algorithmically at least suggests that the Newtonian question, does ball A ever collide with ball B, that I initially posed, cannot be answered algorithmically either. In fact, the Newtonian problem is a much more awkward one than that put forward by Fredkin and Toffoli. They were able to specify the states of their model in terms of discrete parameters, that is, in terms of on or off statements, like either the ball is in the channel or it is not. But in the full Newtonian problem, the initial positions and velocities of the balls have to be specified with infinite precision in terms of coordinates which are real numbers rather than in this discrete way. Thus, we are again faced with all the problems that we had to consider when in chapter 4 we addressed the question of whether the Mandelbrot set is recursive. What does computable mean when continuously varying parameters are allowed for the input and output data? The problem can for the moment be alleviated by supposing that all the initial position and velocity coordinates are given by irrational numbers. Recall that a rational number is a quotient of two integers and is therefore specified in discrete finite terms. Using rational numbers, we can approximate as closely as we like whatever initial data sets we are choosing to examine. It is not altogether unreasonable to guess that with rational initial data, there may be no algorithm for deciding whether or not A and B will eventually collide. This, however, is not really what one would mean by an assertion such as the Newtonian billiard ball word is not computable. The particular model that I have been comparing our Newtonian billiard ball word with, namely the Franklin-Toffoli billiard ball computer, does indeed proceed according to a computation that, after all, was the essential point of Fredkin and Toffoli's idea that their model should behave like a universal computer. The kind of issue that I am trying to raise is whether it is conceivable that a human brain can, by the harnessing of appropriate non-computable physical laws, do better in some sense than a Turing machine. It is of no use trying to harness something like, if ball A never meets ball B, then the answer to your problem is no. One might have to wait forever in order to ascertain for sure that the balls in question never do meet. That, of course, is just the kind of way that Turing machines do behave. In fact, there would seem to be a clear indication that in an appropriate sense, the Newtonian billiard ball word is computable, at least if we ignore the problem of multiple collisions. The way in which one would normally try to compute the behavior of such a word would be to make some approximation. We might imagine that the centers of the balls are specified as lying on some grid of points, where the lattice points on the grid are just those whose coordinates are measured say in hundredths of a unit. The time also is taken as discrete. All the allowed time moments are to be multiple of some small unit, say denoted by delta t. This gives rise to a certain discrete possibilities for the velocities difference in positions lattice point values at two successive allowed time moments divided by delta t. The appropriate approximations to the accelerations are computed using the force law, and these are used to enable the velocities and hence the new lattice point positions to be computed to the required degree of approximation at the next allowed time moment. The calculation proceeds for as many time moments as will preserve to the desired accuracy. It may well be that not many such time moments can be computed before all accuracy is lost. The procedure is then to start again with a considerably finer space grid and somewhat finer division of allowed time moments. This allows a greater accuracy to be achieved, and the calculation can be carried further into the future than previously before accuracy is lost. With a finer space grid still and a finer division of time interval, the accuracy can be still further improved and the calculation projected still farther into the future. In this way, the Newtonian billiard ball word can be computed as closely as desired in ignoring multiple collisions, and in this sense we can say that a Newtonian word is indeed computable. There is a sense, however, in which the word is non-computable in practice. This arises from the fact that the accuracy with which the initial data can be known is always limited. In fact, there is a very considerable instability inherent in this kind of problem. A very tiny change in the initial data may rapidly give rise to an absolutely enormous change in the resulting behavior. Anyone who has tried to pocket a billiard ball by hitting it with an intermediate ball that has to be hit first will know what I mean. This is particularly apparent when successive collisions are involved. But such instabilities in behavior can also occur with Newtonian gravitational action at a distance. The term chaos and chaotic behavior is often used for this type of instability. Chaotic behavior is important, for example, with regard to the weather. Although the Newtonian equations governing the elements are well known, long-term weather prediction is notoriously unreliable. This is not at all the kind of non-compatibility that can be harnessed in any way. It is just that since there is a limit on the accuracy with which the initial state can be known, the future state cannot reliably be computed from the initial one. In effect, a random element has been introduced into the future behavior, but this is all if the brain is indeed calling upon useful non-computable elements in physical laws. They must be of a completely different and much more positive character from this. Accordingly, I shall not refer to this kind of chaotic behavior as non-computability at all, preferring to use the term unpredictability. The presence of unpredictability is a very general phenomenon in the kind of deterministic laws that actually arise in physics, as we shall shortly see. Unpredictability is surely something that one would wish to minimize rather than harness in the construction of a thinking machine. In order to discuss questions of computability and unpredictability in a general way, it will be helpful to adopt a more comprehensive viewpoint than before with regard to physical laws. This will enable us to consider not only the scheme of Newtonian mechanics but also the later theories that have come to supersede it. We shall need to catch some glimpse of the remarkable Hamiltonian formulation of mechanics. Next topic is Hamiltonian mechanics. I will continue this video next time. Take care.